The atom. Well, you've met the atom. You know, it looks like this. Spherical thing, wait, oh, wait, no, nope, that's not it. Hold on, that was Dalton's atom. Wait, no, it looks like this. You know, little spherical thing, positive and negative distributed. Oh, wait, that's not it. No, that was the plum pudding model. That was Thomson's atom. Wait, it's like this. That's it. You know, little positive nucleus, electrons orbiting all around like little, wait, that's not it. Hold on, no, that's Rutherford's planetary model. Okay, hold on. The atom, it looks like this. That's it. Little positive nucleus, electrons orbiting on neat little tracks all around it like planets along the sun that have different energy levels. Wait a minute. That's Bohr's planetary model. That's the Bohr-Rutherford model. Hold on, the atom, it looks like this. There we go. There's the quantum atom. You know, little positive nucleus and a bunch of fuzzy stuff out there which describe orbitals, and the electrons should be somewhere within there. There's a high probability. Yeah, okay. That's it. The atom. I know what you're talking about. Okay, so the atom, well, we've got 3 subatomic particles, right? Yeah, the protons in the nucleus, positive charge. The neutrons, also in the nucleus, no charge. And the electrons outside the nucleus in that big, giant, fuzzy, cotton candy kind of cloud. The atom, that's it. Well, let's talk about these two first. Let's talk about the protons and the neutrons. That is, the things that are inside the nucleus. So, we've got protons and neutrons, and the protons have a positive charge. They have a mass of 1.673 times 10 to the negative 27th grams. Holy cow, is that tiny. And neutrons that have no charge have a mass of 1.675 times 10 to the negative 27th grams. That's also really, really tiny. So here's the weird thing. 2 things that have a positive charge should have what effect on one another? They should run screaming. They should be repelled. But in the nucleus, there are a bunch of protons. And weirdly enough, in the nucleus of atoms, those protons are not repelled by each other, but they're actually attracted by forces that are called nuclear forces. Okay, and the neutrons, they're just sort of sitting there. Atoms are measured most often in picometers. That is 10 to the negative 12th meters. That's really, really tiny. And the radius of the nucleus is about 1,000th of a picometer. That's crazy small. Tiny, tiny. So we can measure how big these things are, but we seldom ever do. It's not really important to us at this level of chemistry. But how massive they are, how much mass they have, that is important. So, did you notice something? Did you notice that the mass of a proton and the mass of a neutron are nearly identical? They're really, really close. When they are 1.673 times 10 to the negative 27th grams and 1.675 times 10 to the negative 27th grams. That's so close that we might as well call them identical. And in fact, we do. So we generalize this a little bit, and we say that one proton has a mass of 1 AMU. Can you guess what an AMU stands for? Remember, particle physicists and chemists are really creative folks. An AMU is an atomic mass unit. So we say that one proton has a mass of 1 atomic mass unit. Well, since protons and neutrons are so darned close to identical, we say that one neutron also has a mass of 1 AMU, 1 atomic mass unit. So, is it fudging the numbers a little bit? It is. But at this level, it really doesn't matter. And if we want to talk about atomic mass, since we've generalized that one proton has a mass of 1 AMU, and one neutron has a mass of 1 AMU, the mass for any atom is just the number of protons added to the number of neutrons. And atomic mass is always given in, you guessed it, atomic mass units, or AMUs. And remember, we are fudging here, and it is okay. Where do I find the mass for an individual atom, you say? Well, I'm glad you asked. You might recall this thing. That's right, the periodic table of the elements. And for every known element, it has an entry on the periodic table. And each of those entries will give you a couple pieces of really vital information. Let's walk through one of them. We'll start off by taking a look at calcium. That's this one. So within each square, you see a symbol. For calcium, it's Ca. And you also see two numbers. The whole number that's very often given above the symbol is the atomic number. The atomic number is equal to the number of protons. So, any element of calcium has 20 protons. That was easy. Any element of chromium has 24 protons. And that number of protons is the identity of the element. If it does not have the correct number of protons, it is not that element. It's something else. Well, that's not the only number in the block. So if we look here, there's another number, which is generally not a whole number, often given below the symbol. This one is a little bit different. It's the atomic mass. And it's given in AMUs, even though no units are specified. So, that atomic mass, it's not a whole number. Oh, I thought you said we couldn't split up an atom. I thought you said we couldn't just randomly lose pieces of an atom. Well, that is true. Kids, there comes a time in life when everyone has to sit down and finally have a conversation about isotopes. It's that time. So, an isotope is most simply an atom of an element that has a different mass. How can it have a different mass? Because though all elements of, let's say, carbon must have the same number of protons, they can differ in the number of neutrons that they have. And because the atomic mass is made up of the number of protons plus the number of neutrons, they can have different masses. So the mass number, which is, remember, the number of protons plus the number of neutrons, minus the atomic number, which is the number of protons, can be used to get the number of neutrons by subtracting one from the other. And isotopes of any element are named for their mass. So carbon-14 is a carbon atom with a mass of 14 AMUs. Would you like to guess what the mass of carbon-12 is? I really hope you said 12 AMUs. So, what's the mass of uranium-238? That's right, kids. It's 238 AMUs. You get the picture. Whatever the number that follows an isotope is, that is the mass of that individual atom. There are 3 different ways to write the name of an isotope. If we write out the name of the element and then after that note the mass, that would be considered writing its full name. We very often use a kind of a shorthand and just write the atomic symbol followed by a hyphen and the mass of the element. That one is called hyphen notation. And the last notation that's sometimes used is what's called symbol notation, where we write the atomic symbol and we write the mass of the isotope in the upper left-hand corner, and we write the atomic number in the lower left-hand corner. This one isn't as common because if we know it's carbon, we know it has 6 protons. This one again is called symbol notation. So, let's practice some of these. You will want a periodic table for this, and you'll want to make liberal use of the pause button. So, let's start off with potassium 40. Write the hyphen notation and the symbol notation. Now's a good time to hit pause. So, from your periodic table, you found that the symbol for potassium is K, and you know that because we're talking about potassium 40, the mass of an atom of potassium 40 is 40 AMUs. Now, for the symbol notation, how's that going to look? In the symbol notation, you're still going to write the K for potassium, and you're still going to write the mass, but the mass is going to go in the upper left-hand corner, and what's going to go below it is the atomic number. In the case of potassium, that's 19, meaning that there are 19 protons in any atom of potassium, including an atom of potassium 40. Okay, we'll practice a few more, and then I'm going to turn you loose. Chlorine 37, write the hyphen notation and the symbol notation. Did you get the hyphen notation right? Hit pause again before I give you the symbol notation. And there it is. The symbol for chlorine, Cl, with a 37 on the top left corner and a 17 below it for the atomic number. Okay, now let's get really tricky. What if I give you the symbol notation and ask you to write the hyphen notation and the full name? Okay, I've given you an O with a 16 and an 8. What would be the hyphen notation? That one you can write without looking anything up. Hit your pause button before I reveal the answer. You could do that without even knowing what this is, because you know that you have the symbol and you know that you have the mass. Obviously it's O16. What's O again? That's what you'll need to write the full name. Hit pause before I reveal the answer. Oxygen 16. That's right. Okay, what if I give you the hyphen notation and ask you to fill in the rest? Here goes. Si29. What is that? Probably helps to go look up Si first. You're going to need the information on the periodic table to complete both the full name and the symbol notation. That's right, it's silicon 29, and while you were looking up the atomic symbol, you probably saw this. That silicon has an atomic mass of an atomic number rather of 14, making the symbol notation for silicon 29 look like this. Si with a 29 in the upper left-hand corner and a 14 below it. Are you pretty comfortable with writing full name, hyphen notation, and symbol notation for various isotopes? Okay, good. Now let's clear up a couple of common misconceptions. A single atom of carbon. Well, the mass given on the periodic table, shown here, is 12.011. So, does that mean that a carbon atom has a mass of 12.011? Wait a second. You said that we couldn't divide a whole atom, so we can't have a decimal. These are weighted averages. You can have a carbon atom with a mass of 12. That would be called what? That's right, carbon 12. You can have a carbon atom with a mass of 13, AMUs of course. That would be called what? Right, carbon 13. Or you can have a carbon atom with a mass of 14 AMUs. That would be called what again? Right, carbon 14. Any one of those can exist, and the atomic mass that you see on the periodic table is an average of all of the carbon atoms that are known to exist in the world. Does that mean that somebody has the thoroughly boring job of measuring every carbon atom on the planet? No, it couldn't be done. It's an average based on the known abundance of the isotopes of carbon that exist. So, though the average mass of carbon is 12.011 AMUs, a single atom of carbon will have a mass of 12, 13, or 14. That mass of an individual atom or of a sample of a given isotope gives you the name of the isotope. So if somebody asks you, what's the mass of a uranium-238 atom, you can look them straight in the eye and say, duh, 238 AMUs, or we'd call it something else. The last thing we're going to talk about is how to fill in a chart that asks for the number of protons, neutrons, and electrons in a neutral atom. Okay, so if you're confronted with a chart like this, which, not to spoil the surprise, you will be, you're given a few pieces of information, and from that you have to deduce the rest. So let's start off with our first example. We have here S32. Well, from the periodic table, you know that S is the chemical symbol for sulfur. And from our work with isotopes, you know that the mass of a single atom of sulfur-32 would be what? That's right, 32 AMUs. Now, from the periodic table, you should be able to get the number of protons that sulfur has pretty easily. 16, and that would hold true for any isotope of sulfur. Now, we're going to skip a column. It's important to remember that here, until specified otherwise, we're always talking about a neutral atom. So in a neutral atom, the number of protons has to be equal to what? That's right, the number of electrons. So in a neutral atom of sulfur-32, if we have 16 protons, we have to have 16 electrons. Now comes the mathy part, and this is pretty low-grade math. If we have a mass of 32 AMUs and 16 protons, how many neutrons does it take to make up the balance of that mass? Well, the mass of any given atom of an isotope is found by adding the number of protons and the number of neutrons. That gives you the mass number. Well, actually, we've got a great cheat here. If we've written the symbol notation like this, we can just turn that into a subtraction problem. And 32 minus 16, of course, gives us 16. So an atom of sulfur-32 would have 16 protons, 16 neutrons, and 16 electrons. Now, that one was easy because I gave you the symbol. Let's look at the next one. This is where we have to do just a little bit of deduction. Remember what we said about the number of electrons and the number of protons in a neutral atom of any isotope. So if the isotope in question has 35 electrons, how many protons does it have? Right, who's buried in Grant's tomb? 35 protons. From this, we can deduce the identity of the atom. So we're now looking at atomic number. 35 protons means we're talking about bromine. And a mass of 79 means we're talking about bromine 79. We can write the isotope in the first column. Now that we've got that established, we can figure out the number of neutrons by subtracting the number of protons from the mass number. Most easily done by, that's right, writing the symbol notation and turning it into a subtraction problem. Okay, a neutral atom of bromine 79 is going to have 44 neutrons. Okay, if we look at our third example, you're given the number of protons and the number of neutrons, but no mass number, no symbol, no number of electrons. Let's work through our process of deduction again. We know that in a neutral atom, protons and electrons are always equal, so it's easy to fill this column in. And we know that mass is equal to the number of protons plus the number of neutrons, so we can fill in the mass column pretty easily. Now, to find what isotope we're talking about, we have to go looking on the periodic table for something with atomic number 8. Aha! That would be oxygen. So here we're talking about an atom of O18, also known as oxygen 18, one of the less common isotopes of oxygen. Okay, the next one is the first one where you've been given a number of neutrons and a number of electrons. So again, we can deduce the number of protons because we are talking about neutral atoms here. So the number of protons must equal the number of electrons. That gives us 18 protons, and we can go looking for what is it that has an atomic number of 18. Argon's our candidate, and we can get our mass by adding 18 and 21. This would have a mass of 39, so we're talking about an atom of argon 39. Okay, 2 more examples, and you'll be cut loose to work on this on your own. Aha, PB207, the big guns. So PB, you have to know, is lead. And of course, since this is PB207, what's the atomic mass? Right, 207. Don't ever miss that on a quiz. Knowing that this is lead means we can go to the periodic table and look up the atomic number for lead. That would be 82. So since we know that a neutral atom of lead-207 has 82 protons, it has to also have 82 electrons. Now getting the number of neutrons is quite simple. Wow, 125 neutrons. That's a lot of neutrons. Okay, last one we're going to do together. We have a mass of 35 and 17 protons. So we go looking on the periodic table for something with atomic number 17. Lo and behold, we have chlorine. So we know that our symbol is Cl. Our mass is 35. We are talking about a neutral atom of chlorine 35. Since it's neutral, we know that protons and electrons must be the same. We have a 17 for the electrons. And our mass, our number of neutrons, of course, will equal 35 minus 17. All right, we have 18 neutrons. That should allow you to easily do the practice sheet, which involves writing isotopes in 3 different formats and completing a table such as this, listing the number of protons, neutrons, electrons, mass, and isotope symbol for any given atom of any isotope.